right? We are going to, the next one is we are going to talk about the normal distribution where normal distribution or Gaussian distribution where x has mean value mu and variance sigma square. So I'll quickly start by writing the probability density function because we've seen as to how to write the um, moment generating function in the previous video. So I'll quickly start with that root over 2 pi sigma square e power minus of x minus mu whole square by 2 sigma square, where x ranges from minus infinity to infinity. This is the probability distribution function of normally distributed random variable x, and I'm going to write the moment generating function here without exponent of expectation of e power tx, which is going to be, because Gaussian is continuous in nature, it's going to be integral e power tx 1 by root over 2 pi sigma square e power minus of x minus mu whole square by 2 sigma square dx. So I'll just introduce again the standard normal variable z. I hope you remember it from the z's course. We've done numerous problems in the classes. So yes, z is x minus mu by sigma. I'll be introducing that temporary variable in here for the ease of working, and then finally getting my moment generating function. So if I differentiate it, it's going to be dx is going to be sigma times dz, and I'm going to substitute the same in there. There's not going to be any change in the limits. I hope you understand that. So 1 by root over 2 pi sigma, I'm going to pull sigma out in here, and this is going to be integral minus infinity to infinity. In place of x, I'm going to get t times mu plus sigma z. I guess yes, isn't it? Mu z plus sigma z plus mu is what x is going to be. I'm going to substitute that over there. And this is going to be e power minus z square by 2. And in place of z, we have dz. Okay, so the sigma in here and in there are going to be cancelled out. And I'm sure we can pull a few constants out. E power mu t is a constant, so I can just simply pull it out. So e power mu t times 1 by root over 2 pi integral minus infinity to infinity e power sigma z times e power minus z square by 2 dz. If you remember, we have landed up with the same situation where we started in the last standard normal distribution, which was e power tx minus x square by 2. It's in the similar lines, and we are going to do a similar thing over here. We're going to add and subtract sigma square t square by 2 to this, and we'll be let me just quickly do without so here I have, these are the things that I have from my previous slide. So what I am going to do is I'm going to add and subtract sigma square t square by 2. So z square plus sigma square t square minus sigma square t square minus tz sigma whole by 2. So I'm going to substitute this over here, and then if I'm simplifying it, I'd be left with, finally, I'll be left with a minus b whole square by 2. I hope you are following it, plus sigma square t square by 2. This is what I'd be left with. All right. So these are the values. So I'm going to substitute them back into my moment generating function. So under root 2 pi e power mu t integral minus infinity to infinity e power sigma square t square by 2 the first one, and then e power minus z minus sigma t. Sorry about that. This is going to be, the brackets are going to be inside, not on the outer side. So let me just quickly write that down. All right, and then e power minus z minus sigma t whole square by 2. It's all right, by 2. This is going to be dz. So this happens to be a constant because the integral is with respect to z. So it's going to be a constant, and the next step is I'll be left with e power mu t times e power sigma square t square by 2, 1 by root over 2 pi integral minus infinity to infinity e power minus z minus sigma t whole square by 2 dz. Right, so this is very well, this very well looks as our Gaussian PDF with the mean sigma t. If you can see, the mean here is sigma t, and variance is 1, right? So we have this, and the area under the PDF of the normal distribution with mean sigma t and variance 1 is going to be unity. So this is going to be unity, leaving us with e power mu t plus sigma square t square by 2 plus sigma square t square by 2. This is what is the moment generating function of a standard norm, sorry, of a normal variable, and we can write the characteristic function from here. So the characteristic function is in place of t, we are going to substitute j omega. So this is going to be j mu omega, and because we have its j square is minus 1, this is going to be, sorry about that, minus sigma square omega square by 2. This is going to be our characteristic function, right? So let's just summarize what we have found out, and I'm not going to worry about finding the mean values here. Mean mean is mu, variance is sigma square, right? And then the moment generating function for the Gaussian random variable x is going to be e power mu t plus sigma square t square by 2, and the characteristic function is going to be e power minus j omega mu minus sigma square omega square by 2, right? So this is the these are the moments, mean and variance of our Gaussian distribution function. So in the next video, we're going to see problems on moment generating function and how to solve them. Right? Thank you all.